Now we're recording. So you need to enter the data, math and physics test. So on L3, I'm going to use L3 to generate x squared, okay? So L3 is gonna be L1 squared. So all we gotta do is go to the top of the L3 and over there, just put second L1 and square it. That will generate all the data in L1 squared. Okay, so that's L3. So I'm gonna put notes here so I know what I'm gonna do in a second. So this is L1, L2, L3. And then in L4, I'm gonna do the same thing for the y values. So I'm gonna put L2, second L2, and square it. So that's gonna be the y values squared, okay? And then the next step in L5, I'm gonna put the product of x times y, which is L1 times L2. So this is L4, L5. Okay, so that's gonna be L1 times L2. And that's all the information we're gonna need, all right? So I don't know if you have taken a look into your book, right? But this is what, this is the coefficient, the correlation coefficient formula that we have to dissect. So R is SXY over SX times XY. So what is all that? All right, so then let me write the formulas here so that that's what we're gonna be doing. So then we have that SXY is given by the sum of the x times y over n minus x bar, which is the mean of the x values, times y bar, which is the mean of the y values. So that's the first thing that we need to get, okay? The second thing is the bottom. The bottom is just the standard deviation for x and y, okay? So the standard deviation for x is gonna be the square root of the sum of the x squares over n minus the mean x bar squared, okay? And then the standard deviation of the x values, of the y values is the same thing, but for the y values. The sum of y squared over n minus the y mean squared, okay? So look, if you were going to do this by hand, all right, in your IA, you just need to basically create this table and show where these things come from. So you cannot say like, oh, running the regression, I got this or the other. You actually have to show how it's done. Obviously, I don't have the time to do that every little thing by hand. So I'm gonna use the calculator to illustrate these things, okay? So before I start, I'm gonna find the X bar and I'm gonna find the Y bar, which is just the mean, right? So X bar is just the mean of the X values. So it's the sum of the X values divided by N, and the Y bar is just the mean, right? The sum of the Y values divided by N, all right? So I'm gonna use the calculator to find these values, okay? So I need the mean of the X values, all right? So without running one variable statistics or any of that, so one way that I accomplish that is this. I can go to second stat, which is list, okay? And I can go to the operation, and then I can, I'm sorry, no operations in math. And then I can find the mean. You see, I can find the mean of L1, which is the mean of the X values, okay? So the mean of X1, which is the X values, is 35.72. In the same way, I can find the mean of the y values. So the mean of the y values is in L2. So then the mean of that is 35.08. All right. So I have that. Now I need to find what will this be? This. That's the mean of the products, right? Because it's the sum of all the products divided by n. So where did we put the products? In L5, right? So I'm going to do that here. So I'm going to do this, right? L5. So that would be the mean of that, okay? So I have all the information to find this value, correct? Have this mean, and I have these two means, correct? So S of xy is going to be equal to the first value, which is this, 13, 11, sorry, 11.2, that's that, right? Minus 35, let me move this out of the way, 35.72 times 35.08. And that's going to be the numerator of my coefficient correlation, right? So that's going to be the following. So it's going to be this minus 35.72 times 35.08. And that's giving me 58.1424. So that is 58.1424. So that's the numerator of what I need. And then I'm going to find these two. Okay. Now, for those, that is just the standard deviation of the x values and the standard deviation of the y values, correct? I'm going to do that with the calculator, just to save us some time. All right. So standard deviation, second list math, standard deviation is number 7. So the standard deviation of the x values, so that's L1, 8.72. Okay. And in the same way, I'm going to find the standard deviation of the y values, which is going to be what is the data in L2. Okay. So standard deviation of L2, 8.42. Okay. So what else do I need? That's all I need, correct? So once I have this, then now my coefficient correlation is going to be given by this value, 58.1424, divided by the product of these two values, 8.72 times 8.42. Okay, so let's do that. Sorry. Let's do that. So that's going to be 58.1424 divided by this product, 8.72 times 8.42. And that's what I'm getting. And that's not what I got on my first example. Maybe I did something incorrectly there. Because I'm supposed to get something really close to, oh, okay, I understand where my error is coming from. That's okay. I'm gonna leave it like that, 0.791. Okay. Now, if I run the one variable statistics, okay, let's do that, and let's just compare this value with what we got. So I'm gonna go to stat, calculate, and in this case, let me see. That's not. Wait, what am I doing with the calculator in order to get the standard deviation of x, y? So two variable stat, L1 and L2, not one variable stat. I have two variables, right? The math and the physics. So I'm gonna run this thing. And the standard deviation is I'm doing something wrong with this thing. It's 0.8. What am I doing wrong? Let me show you something, okay?
Was there a reason why we didn't use L3 and L4?
We did use L3 and L4. Oh, that's my error. Thank you, Benjamin. I'm supposed to find the sum of the x squares and the sum of the y squares. I did not, okay? I did the sum, so I believe that's my error there. Let me see. Right, that's the error. So I'm gonna show you something. Thank you, Benjamin. All right, because I was looking at, I obviously did it before class, and I was getting different results. So let me show you this, okay? All this is exactly what I was doing with you guys. The X bar, the Y bar, the value of X, Y, notice that is the same that we got. My mistake in class is that I was not doing the squares, the X squares. I was not doing this. I was not using the X squares. If I have used the L3 and L4 correctly, then S of X squared is this, and S of Y squared is this value. Since I need on the formula, I need S of X and S of Y, I have to take the square root of those two values, which is what I did here, okay? If I do that, then I get 0.82, I'm sorry, 8.24. No, 0.82, I get that, okay? And if you look at this and the standard deviation of the problem, the standard deviation is 8.4. So there is a discrepancy in the values, right? This should be 8.2, not 0.82. The discrepancy in the values is because I'm not using all the decimal places that the calculator actually uses for it, okay? So that will be the error or the difference between what I did here and what the calculator would show, okay? But the error then was that I was not using the X square values, okay? I was just using the X values and the Y values. That was my error in what I just said. So I hope that doesn't confuse you a lot. All right. Example 3. I don't know, is there any question or comment about this? All right, so example 3 says a student obtained a mark of 39 on the math exam, but was absent from the physics exam. Justify the data and the regression line equation from example 1 to predict the grade. Okay, so on example 1, we found this equation as the regression line. We found 0.7965x plus 6.630. That's from example 1. That's the regression line. Okay, so let's look at part A. Part A says that we know the mark for math, but we don't know the physics exam mark, right? So how could I get the physics exam? Remember, X stands for the math marks, Y stands for the physics. So one way to do that is to plug in into the regression equation the math score, which Y of 39. If we plug that in there, then we get an approximated value of 37.69. Let's say we get 39.69 and we approximate that to 38 marks on the physics exam. Okay, so now they're asking the following: justify using the data. So what will this be? So basically they're asking, is this reliable or not? Okay, so so the first thing you have to look into is the X value you're using, okay, or the math score. If you look at the table that was given to us in example 1, 39 is in between those values. So what I mean by that is the following. What I mean is this, that 39 is a value that is in between 20 and 50. It's somewhere in there, right? So it's in the range of the scores that we can, a student can obtain during the test. So, which implies that this will be fairly accurate. Why? Because the X values are in the range of the score. So since 39 is in the range of scores, then Y being about 38 marks is an accurate prediction. So in other words, if you look at the table, the lowest score is 20, I believe, or 8. Let me see. Let me take a look at that. Yeah, it's 20. The lowest score is 20 in the math, and the highest is 50, right? So if the score is less than 20 or more than 50, then our approximation value is not accurate, okay? And that's basically what part B is talking about. Since 39 is in the range of the scores, so what we just did is called interpolation. And the word inter means is inside the range, okay? Part B is asking if another student was absent from the math exam and his grade on the physics exam was 15, state the reason whether it is justifiable to predict this math grade using the regression equation. So is 15 a physics score in the range of scores that we have?
No.
It's not, right? The physics score, the lowest score is 18, and then the highest score is 48. So 15 is not in that range, which implies that any approximated value using this regression line will not be accurate because it's outside that range. So Y of 15 is not an accurate prediction because 15 is outside the range of scores. Okay, so B is what we're called extrapolation. Most of the time, extrapolation is an inaccurate approximation unless the problem tells us that the values outside the range behave in the same way. Does it make sense? Because because this regression line works with the values that are given to us. We cannot assume that the same behavior is going to happen outside those ranges. Does it make sense? So that's why interpolation is going to be always accurate if it's inside the range, but extrapolation is not going to be accurate. Make sense? What that means? All right. And I repeat, unless the problem tells you that outside the given values, the behavior is the same, then an extrapolation will be fine. So here it says, a value predicted from within the smallest and largest value is called interpolation. That's what we did on part A. The accuracy of interpolation depends on how the linear data is. This can be gauged by the correlation coefficient. Obviously, if the correlation coefficient is if the correlation is weak, then whatever approximation value I use with this regression line is not going to be accurate, right? Because the regression is weak. The accuracy of extrapolation, that means outside, depends on not only the original data, but also assumes that the relationship extends outside the data we have collected, meaning that the relationship is the same outside those data, those values. This depends on the situation under investigation and is unlikely to be reliable. So extrapolation most of the time is not a good thing, right? Because we don't know how the data behaves outside the data set that we have. All right, so let me see. And we're about to finish this thing. Correlation versus causation. Just because two variables are correlated, that doesn't mean that one causes the other, okay? That's important. So it says here, a scatter graph often shows a relationship between two variables of a data set correlation. However, this does not imply that a change in one variable causes a change in the other. For example, it is not a good explanation of the relationship between run 1 and run 2 of the sky race to say that the time in run 2 was slow because the time in run 1 was slow. So the main thing there is the following. Just because there is a correlation, it doesn't mean that one variable is affecting the other, okay? It may not be the case. Correlation is only linear. Using the correlation coefficient as a measure of correlation only allows the recordings of linear correlation, okay? So a quadratic regression, a cubic regression, a logarithmic regression, on that, we're not talking about correlation. So the correlation is only for linear. The fallacy.
Mr. Francis,
Yes, sir.
I have a question. If we find a correlation between x and x squared, can we use x squared to like y squared to find the linear correlation with x?
Say that again.
If we want to find the correlation between x and y squared, can we find the linear correlation between x and y squared?
Yeah, there are methods to let's say establish a correlation between something that doesn't behave linearly. There is a method to do that. What this is saying is that the correlation coefficient that we establish for this data that we work with is mostly linear, okay?
Okay.
So other method will be used in terms of if we have a different type of regression, okay?
Okay.
Sometimes it says that the fallacy of this fallacy is very common, and what this means is that there might be a correlation between two variables, okay? But one is not causing the other. There is a third variable that plays a role that not necessarily shows into the data that we gather, okay? So what that means is that what is called lurking variable is something that is hidden that is affecting the relationship that we're trying to establish, okay? Let me see. So it is essential to ascertain whether there is a mathematical relationship between the variables, which might give a rise to an invalid correlation. For example, if a relationship is required between a student's math HL grade and a total diploma points, because the math grade from part of the total diploma grade, then careful examination must be made before the correlation analysis can be applied. So this is saying the following, that in this example of the IB diploma, the total diploma points, well, math is just one part. So math cannot just be just the only predictor of the diploma points. Does it make sense? Because there are other courses to take into consideration. That's what that is saying. It says combinations from separate populations. It is essential that the data set arise from homogeneous populations rather than two distinct groups. So if we're comparing populations in a way, so that we have to determine that those populations are as close to each other as possible. Okay, that's what it means, homogeneous, the same type of populations. Incorrect sampling techniques. So if the sample that we collect is not a fair representation of the population, so whatever conclusion we get to is going to be incorrect. Okay. So, all right, that ends our class. The part of the what I needed to share with you. I apologize again for the mistake I made on the first